We're going to start by taking a review of what we did last time. Last time we built a differential amplifier using BJTs, discrete transistors. And if you'll remember, we started out with a pair of matched NPN transistors. Oh, let's just pick some voltages, plus 15 volts. Those transistors had their emitters connected together. We put some resistors in series, but we didn't have to because we have the intrinsic RE of the BJT, little re. We had current going down either through a resistor or a current source. So a bias current. Two inputs. The output was going to be the difference between the two of them. Actually, we called this I tail. And at quiescent, when both inputs were at exactly the same voltage, we had 1/2 of I tail flowing through each collector. And that makes sense. If these transistors are exactly the same and the voltages at the bases are the same, then their base emitter voltage drops are going to be the same, and this current is going to divide equally. We then added a high gain stage using a PNP. And we tended to use either current sources or resistors, but in the final design, current source give us more gain because our gain is the little emitter resistor divided into whatever the collector resistance is. And of course, a current source has very high impedance. The only problem is that the output impedance at this stage is the impedance of the current source, very high, and also the collector impedance of the transistor, also very high. So we need some way of getting lower output impedance, and we did that using a pair of BJTs in what's known as a push-pull stage. And if you think about it, what this really is two emitter followers. This one is emitter follower that provides positive current from the plus 15 volt supply, and this one can sink current into the negative supply. So we've got three stages. We have our differential input stage. We have our gain stage, and then we have an output buffer. And a buffer just reduces the output impedance and allows us to get a reasonable amount of current. So it has a low output. What was nice about this was, unlike the single transistor amplifiers we looked at before, where we always had a VBE drop, so if we put a voltage at our base, the emitter was either 0.6 volts lower or 0.6 volts higher. We always had this DC offset. Here we have an amplifier where the DC drop of the emitters from base to emitter are, here we have a drop down, but we have a drop up. So the difference between these voltages is all we care about. If we were to ground one of these, we'd have a single-ended amplifier, and it would be referenced to whatever voltage this was at, in this case ground. So if this was at 0 volts, our output would be 0. If it goes positive, the output would go positive. If it goes below ground, we would go negative on the output. So we've gotten rid of the offset. In addition, there's other temperature effects as the VBE changes with temperature. If these two transistors are built on the same die, their VBE changes at the same rate. And so even if the die heats up, we don't get big output swings the way we did before. So we don't have to worry about the fact that we don't have a big RE in here. So this was a simple operational amplifier. You built this. But it turns out that this is so useful that we can get them already built for us. So we have something called an operational amplifier. Usually abbreviated op-amp, sometimes even OA. This is a 5-terminal device. We have a positive input, we have a negative input, we have an output, But it requires power. So we have a positive power supply and a negative power supply. VCC, VEE. CC is sort of like collector, EE is emitter. Think about an NPN transistor. Current flies from plus to minus. Now, normally VCC is a voltage above ground. We're going to use plus 15 volts most of the time. VEE is a voltage below ground. We're going to use minus 15 volts. It doesn't have to be. There just has to be a voltage difference from VCC to VEE, where VCC is more positive, to provide power. Now, we're limited. The inputs and the outputs can't be greater than VCC and less than VEE. So it turns out that if we use split supplies, which is to say a positive voltage for VCC, a negative voltage for VEE, it works with signals that are both positive and negative. So that's what we're going to do initially. Later on in a couple lessons, we'll talk about how to use this with a single supply. This is very similar. We did an emitter follower where we connected the emitter through a resistor to a negative supply, and that allowed our output to go negative. One thing to remember about this device is you always have to apply power to it. So make sure you do that. Now, in this class, we're going to be using some op amps, an LF411, an LM358, LM741. There's no standard naming convention. Sometimes they're OP. It depends on the manufacturer. The thing to remember is they usually come in an 8-pin package. Sometimes you'll get one in a package. With the 411, you get one. The LM358 has 2 in a package, so if you're building something complicated, you may prefer to use that. There's hundreds of different types of op amps. They all have different specifications, but we're not going to get into those details until a later lecture. So what does this thing do? Well, what's in here is essentially this differential amplifier, a little fancier version than the one we did. And we can model this as first a circuit that subtracts V minus from V plus. So that gives us an output that's V plus minus V minus. That goes into a gain stage with a gain of A. This is usually pretty big, on the order of 10 to the 5th to 10 to the 6th. And then that goes into essentially a limiting circuit. So if we think about V in versus V out, we're going to have gain up until some point, and then we saturate, and we're going to saturate around VEE to VCC. We can't go higher than VCC, and we can't go lower than VEE, and that should make sense. There's transistors in there, and the transistors can't put out more voltage than they're powered by. And that gives us our V out. So this is our model for our op amp. Now, this is actually very steep. This is not to scale. Clearly, if I put in a very small voltage here, I'm going to get a big voltage out there because of this high gain. And that's what we're going to do in our very first lab today. So what I want you to do is take quiz 1. Quiz 1 is pretty short. Spend 5 to 10 minutes on it. When you're done with quiz 1, we're going to go into the lab, and we're going to do the first 2 parts of the lab. It's essentially one part, which is through lab 6, part 2. If you have any questions either on the quiz or on the lab, raise your hand. We're here to help. The whole idea of the Verse Classroom is we'll take little bites out of this stuff, and hopefully that'll be a lot easier than getting all the information in advance, trying to keep track of it, and then going into the lab and work on it. So when you're done, make sure you ask some questions. Come back, sit down, watch the next part. We'll first go over the quiz. We'll talk about what you did in lab, and then we'll move on to how we actually use these devices, operational amplifiers and circuits.